Hello there, and welcome to the Sleepy Science Channel. Tonight, we are stepping into one of the greatest adventures of all, a journey into cosmic mysteries. Above us stretches a universe that is vast beyond intuition, filled with forces we cannot see, energies we barely understand, and questions that have challenged every generation that has looked up at the night sky. We will wander through dark matter and dark energy, through black holes that bend reality, and through the faint afterglow of the beginning itself. We will consider worlds that drift without stars, signals that flash across billions of light years, and puzzles that remain unsolved even now. The cosmos is not only enormous, it is strange, dynamic, and still unfolding. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing you need to do. Let your breathing slow. Let your shoulders soften, and allow your thoughts to drift outward, as vast and open as space itself. And as your body settles and your mind begins to wander, we will explore these mysteries together. Let's begin. Most of the universe is invisible, and we do not know why. When you look up, your eyes are catching a tiny sliver of what exists. Light is only one kind of messenger, and the cosmos uses many others. There are radio waves, infrared heat, ultraviolet glare, X-rays, and gamma rays. There are also things that do not shine at all, yet still shape the universe with their gravity. Even the bright parts can vanish behind dust or get stretched into wavelengths our eyes cannot see. So every telescope is a kind of translator, turning hidden signals into pictures and graphs. The strange part is how much remains missing even after we build better translators. When astronomers add up everything that should be there, stars and glowing gas are only a small fraction. The rest acts real, but stays unseen. We can see only a bubble of the cosmos. The universe may be far larger than what we can observe, or it may even be infinite. Either way, there is a hard limit to what can reach us. Light takes time to travel, and the universe has a finite age. That means there is a horizon, a boundary beyond which signals have not had time to arrive. The boundary is not a wall in space. It is a boundary in time and distance combined. Even stranger, expansion can carry regions away so quickly that their light will never catch up, no matter how long we wait. So the visible universe is like a lighthouse beam in fog. It shows a region around us, bright with information. Beyond it, the cosmos could continue with more galaxies, more voids, and perhaps surprises that we cannot yet imagine. The Big Bang began everywhere at once, not in one place. It is tempting to picture an explosion that happened at a single point, sending matter outward into pre-existing emptiness. The real story is more subtle. The Big Bang describes a time when the entire universe was hot and dense, and then space itself began to expand. Every region was once compressed, and every region took part in the stretching. A helpful image is rising bread with raisins. The raisins move apart, not because one raisin is the center, but because the dough between them grows. From any raisin, all the others appear to recede. That is why distant galaxies seem to be moving away in all directions. There is no unique starting location you can point to on a map. The beginning was not a place. It was a state of the whole universe, everywhere at once. Dark energy seems to be speeding up cosmic expansion. For a long time, many people assumed the universe should be slowing down. Gravity pulls, so expansion ought to lose momentum like a tossed ball. Then teams studying distant exploding stars found something unsettling. Those supernovas looked dimmer than expected, which suggested the universe had stretched more than it should have. The simplest reading was that expansion is accelerating. It was a discovery that changed cosmology overnight, because it implied a push built into space itself. Some call it dark energy, but the name is a placeholder, not an explanation. It might be a constant energy of empty space, or it might be a new field that changes over time. Either way, it shapes the ultimate fate of everything. Dark matter holds galaxies together, yet it has never been directly detected. Galaxies spin in a way that should tear them apart. If you only count the stars you can see, the outer regions move too fast to stay bound. Something unseen provides extra gravity, like an invisible scaffold holding the whole structure steady. The clue appears again and again in galaxy clusters, in the bending of light called gravitational lensing, and in collisions where hot gas separates from the main mass. Experiments on Earth have tried to trap the particles directly, deep underground, in icy detectors and in massive tanks of ultra-pure material. So far, there is no confirmed catch. That makes the mystery sharper. We can trace its fingerprints across the sky, yet the substance itself refuses to show its face, even in our most careful traps. The universe has an afterglow you can detect with antennas. Long after the first light of stars, the universe still carries a much older light. It arrives from every direction with nearly the same strength, like a cosmic whisper that never stops. It was found by accident when two engineers tried to remove persistent noise from their radio equipment. The signal did not fade, and it did not come from any one place. It was the cooled-down remnant of the hot, early universe, stretched by expansion until it became microwave radiation. Today, it is measured from balloons, ground stations, and spacecraft, with extraordinary precision. Tiny temperature variations form a delicate pattern, and that pattern encodes the seeds of future galaxies. This afterglow is one of the strongest pieces of evidence that the universe began hot, dense, and changing fast. Time runs differently near intense gravity, and we can measure it. Gravity is not only a pull, it is also a change in how space and time behave. Near a massive object, time passes more slowly compared with time far away. This sounds like science fiction until you realize it affects everyday technology. Satellites carrying atomic clocks tick at a slightly different rate than clocks on Earth. If engineers ignored that shift, navigation systems would drift off course by kilometers. The effect is also seen in experiments that compare clocks at different heights, even within a single building. The deeper you sit in Earth's gravitational field, the more slowly time ticks. It is a reminder that time is not a single universal river. It is a fabric that can stretch and compress. The universe keeps time in many local rhythms, and gravity is one of the conductors. Black holes warp space so strongly that light can orbit. Light usually travels in straight lines, but gravity bends the path by curving spacetime. Around a black hole, that curvature becomes extreme. There is a region where light can circle the hole, not forever in a stable path, but long enough to create dramatic effects. This is part of why black holes can cast a shadow, even though they emit no light of their own. It is also why matter falling inward can look strangely bright. The hot gas in an accretion disk races around at enormous speeds, and its light is bent and boosted on its way out. When the Event Horizon Telescope produced an image of a black hole's shadow, it was not a photograph in the ordinary sense. It was a map of warped light, shaped by gravity so strong that even photons must curve. A black hole's center might hide physics we cannot describe. General relativity predicts that, deep inside, gravity can compress matter without limit. In the mathematics, density becomes infinite, and space and time break down. Physicists call that a singularity, but it is better thought of as a warning label. It marks a place where our current equations stop giving sensible answers. Quantum physics should matter there, because the scales become extremely small. Yet we do not have a complete theory that unites quantum rules with gravity. That leaves a gap right at the heart of one of nature's most dramatic objects. Some ideas propose that the core is replaced by a quantum structure, or a region where space-time becomes foamy, or a bounce into a new phase. No one knows. The center of a black hole might be the most honest sign that our map of reality is unfinished. The universe may be flat, which is deeply mysterious. Flatness here does not mean two-dimensional. It means the large-scale geometry of space may have zero overall curvature. In a curved universe, the rules of geometry change. Triangles can have more or less than 180 degrees, and parallel lines can meet or spread apart. Measurements of the cosmic microwave background suggest that, across enormous distances, space is very close to flat. That is surprising because curvature tends to grow with time, unless the starting conditions are tuned with astonishing precision. It is as if the cosmos began balanced on a knife edge. Inflation is one possible explanation, because rapid early expansion would smooth away curvature like stretching a wrinkled sheet. Even so, the question remains: why should the universe have begun in a state that becomes so close to geometrically flat at all? It is a simple result, with a profound backstory. Quantum fluctuations may have seeded every galaxy you see. At extremely small scales, quantum physics tells us that empty space is never truly empty. Fields fluctuate constantly, producing tiny variations in energy. During a period of rapid expansion, those microscopic fluctuations could have been stretched to cosmic scales. What began as subatomic jitters would then become slight density differences across vast regions. Over time, gravity would amplify those differences, turning them into the large-scale structure of the universe. The idea is both humbling and astonishing. The majestic spiral galaxies in the night sky may trace their origins to quantum noise. Observations of the cosmic microwave background show a pattern of fluctuations that matches this picture remarkably well. It is a bridge between the smallest and largest realms, suggesting that the architecture of the cosmos grew from the restless behavior of quantum fields. Space might have grown from a quantum event. Some approaches to quantum gravity suggest that space-time itself is not fundamental. Instead, it may emerge from deeper quantum ingredients, much like temperature emerges from molecular motion. In certain models, the universe could have begun as a quantum transition, perhaps from a prior state or from a fluctuation in a broader framework. These ideas remain speculative, yet they are taken seriously in theoretical research. They attempt to remove the singular beginning predicted by classical equations and replace it with a process governed by quantum rules. If spacetime can arise from something more basic, then what we call reality might be a large-scale manifestation of microscopic relationships. This perspective changes the question from what happened at the beginning to how the concept of beginning itself emerges from quantum structure. Scientists still do not know what dark matter is made of. Across the world, detectors sit in deep mines, under mountains, and beneath thick layers of rock, all waiting for a faint interaction that may never come. The idea is simple. If an unseen particle drifts through Earth, it might occasionally nudge an atom and produce a tiny flash of light or heat. So far, the silence has been profound. Particle accelerators have searched for new candidates, while space telescopes scan for indirect signals that could betray its presence. Each null result narrows the possibilities, yet the mystery remains open. It could be a new kind of weakly interacting particle, It could be something far stranger, woven into space-time itself. The remarkable part is that galaxies depend on it. The cosmos behaves as if this substance is abundant, yet in the laboratory, it remains a ghost. Some theories predict dark matter can annihilate into light. If the unseen particles have antiparticles, then pairs might collide and convert their mass into energy. That energy would emerge as gamma rays or other high-energy signals. Astronomers search places where the invisible mass is thought to be dense, such as the centers of galaxies or small satellite galaxies orbiting the Milky Way. They look for an excess glow that cannot be explained by known sources. There have been hints, debated signals that stir excitement, then caution. The challenge is that space is messy. Pulsars, supernova remnants, and hot gas can all produce similar radiation. Untangling the source requires patience and sharper instruments. If such a signal were confirmed, it would be the first time we watched the dark sector light up the sky, turning a hidden component of the universe into something briefly visible. The missing antimatter problem still has no final answer. According to basic physics, the early universe should have produced matter and antimatter in nearly equal amounts. When matter meets antimatter, both vanish in a burst of energy. If the balance had been perfect, everything would have annihilated, leaving only radiation behind. Yet stars, planets, and people exist. That means a tiny excess of matter survived, perhaps one extra particle for every billion pairs. Experiments at particle accelerators have found subtle asymmetries in certain decays, small violations of symmetry that favor matter slightly. But the measured effects do not seem large enough to explain the cosmic imbalance. Something more must have happened in the hot early moments. The puzzle is profound because it connects the smallest scales of particle physics to the existence of galaxies. Our presence is tied to an ancient asymmetry that remains only partly understood. We do not know why there is more matter than antimatter. This question reaches back to the first fractions of a second. For an imbalance to develop, three conditions are required. Certain reactions must violate barrier number. Physical laws must treat matter and antimatter differently, and the universe must pass through stages out of Chinju, thermal equilibrium. Physicists can describe these requirements clearly, yet the exact mechanism is still uncertain. Some ideas involve heavy particles that no longer exist, which decayed in a way that favored matter. Others look to processes linked with neutrinos and their unusual properties. Experiments are probing these possibilities with increasing precision, searching for rare events that hint at deeper asymmetries. The reason this matters is simple. Every atom in your body is evidence that, long ago, the cosmic scales tipped slightly in one direction. The cause of that tiny tilt remains one of the great open stories. The cosmic microwave background contains tiny birthmarks of galaxies. When the early universe cooled enough for electrons and protons to combine, light was finally free to travel. That light carries a record of conditions at that moment. It is astonishingly uniform, yet not perfectly smooth. There are minuscule temperature variations, differences of only a few parts in 100,000. Those faint ripples represent regions that were slightly denser or slightly thinner than average. Over billions of years, gravity amplified those initial differences. Dense regions drew in more matter and eventually formed galaxies and clusters. The pattern in the sky today is like a baby picture of cosmic structure. By mapping it with exquisite detail, scientists can test models of the early universe and measure key properties such as its composition and geometry. From subtle variations in ancient light, we reconstruct the blueprint of everything that followed. One cold patch in the cosmic background remains unexplained. Among the otherwise even pattern of ancient radiation, there is a region that appears slightly cooler than expected. It spans a surprisingly large area of the sky, and its origin is debated. One idea suggests that light passing through a vast cosmic void could lose a bit of energy, creating a colder imprint. Another possibility is that it is simply a statistical fluke, an unlikely but not impossible variation in a random field. More speculative suggestions involve exotic physics in the early universe. Careful measurements have confirmed that the feature is real, yet its interpretation remains open. What makes it fascinating is that it sits within our most precise cosmological data set. Even in a map measured to extraordinary accuracy, there are still anomalies that resist tidy explanations, reminding us that precision does not eliminate our mystery. Inflation may have stretched space faster than light could travel. In the earliest instance, the universe might have undergone a brief episode of explosive expansion. During this phase, space itself would have expanded at an extraordinary rate, so rapidly that distant regions separated faster than light could move through space. This does not violate relativity because nothing traveled through space faster than light. Instead, the fabric itself expanded. Inflation helps explain why the universe appears so uniform across vast distances, since regions now far apart were once close enough to share conditions. It also predicts a nearly flat geometry and a specific pattern of tiny fluctuations. The idea is elegant, yet direct evidence remains indirect. Scientists search for subtle polarization patterns in the cosmic microwave background that could reveal primordial gravitational waves. A confirmed signal would offer a glimpse into a moment unimaginably early in cosmic history. No one knows what triggered inflation or how it ended. Even if rapid expansion occurred, the mechanism behind it is uncertain. Many models propose a hypothetical field with a high energy state that drove the expansion. As the field evolved, its energy would have been released, reheating the universe and filling it with particles. The details vary widely from model to model. Some predict distinctive signatures in the distribution of cosmic structures. Others suggest rare relic particles might still linger. What remains unclear is why inflation began in the first place, and why it stopped when it did. These questions push into territory where quantum physics and gravity intertwine. Without a complete theory of quantum gravity, we are exploring with partial maps. Inflation may be the best framework we have for early expansion, yet its engine is still hidden behind a veil of theoretical possibilities. The Hubble constant has two measurements that stubbornly disagree. One method uses the nearby universe like a set of stepping stones. First, you measure distances to certain pulsating stars. Then you use those to calibrate brighter objects like supernovas. Then you extend outward. Another method looks at the oldest light in the universe and uses a physical model to infer how fast expansion should be today. Both approaches are careful, both have improved, and yet they land on noticeably different answers. That gap is called the Hubble tension, and it matters because it could be a clue that something is missing from our cosmic story. Maybe the early universe behaved differently than we assume. Maybe there is an unknown particle, an extra interaction, or a subtle bias still hiding in the data. Either way, the disagreement is not a nuisance. It is a doorway. The first stars may have been massive and short-lived. Before stars existed, the universe was mostly hydrogen and helium, with almost none of the heavier elements that help gas cool and fragment. In that simpler chemistry, clouds could have collapsed into fewer pieces, which hints that the earliest stars were enormous. They would have burned fuel at a furious pace, shining intensely, then dying quickly on cosmic timescales. Their ultraviolet light would have changed their surroundings, carving bubbles in the dark, and their deaths would have scattered the first heavy elements into space. That enrichment would have altered everything that formed afterward, from later stars to the first rocky ingredients of planets. We do not have a photograph of one of these pioneers. Still, their fingerprints may be written into the composition of ancient gas and the chemistry of the oldest surviving stars. The first starlight may have been brief, but it rewrote the universe. We have never directly observed a true first-generation star. Astronomers call them Population 3, stars made from pristine material that had never been touched by a previous stellar life. Finding one is hard for two reasons. First, they would have lived fast and died young, so most should be gone. Second, they would have formed at enormous distances and at very early times, so any surviving light is faint and stretched. Instead, we hunt for indirect evidence. One approach is to search for stars in our own galaxy that are extremely low in heavy elements, because their chemistry can hint at what came before. Another approach is to look for distant galaxies with unusual spectral signatures that suggest very hot, metal-poor stars. So far, every candidate has a catch. The dream discovery would be a clear signal of a star with no metals at all. It would be a direct glimpse of cosmic dawn. The earliest galaxies formed surprisingly fast, and Webb keeps finding more. In the usual picture, the first galaxies should be small and gradual, built up over time from simpler clumps. Then observations began to show bright structured galaxies at times when the universe was still very young. Some appear to have grown stars quickly, and some look more massive than we expected so early. These discoveries do not automatically overturn the story, but they do apply pressure. If galaxies assembled rapidly, then gas must have cooled efficiently, stars must have formed quickly, and black holes might have started feeding early as well. It also forces a closer look at how we interpret distant light, since estimating distance depends on subtle features in a spectrum. Either way, it is thrilling. Every new deep field is like opening a fresh chapter in a book we thought we already knew. The early universe is revealing itself as more productive and more surprising. Reionization ended the cosmic dark ages, but details are hazy. After the universe cooled and atoms formed, space became filled with neutral hydrogen that absorbed energetic light. For a time, there were no stars, no galaxies, and no new light sources. Then, the first luminous objects switched on, and their radiation began to tear electrons away from hydrogen again. This process slowly transformed the universe into an ionized, transparent state, where light could travel more freely. That transition is called reionization, and it was not a single moment. It likely happened in patches, with bubbles of ionized gas expanding and merging. We are still learning which sources did most of the work. Was it mostly young galaxies, or did early black holes contribute? We probed this era through distant galaxy spectra and the imprint it leaves on the cosmic microwave background. It is a story of dawn arriving unevenly across a vast sky. Most ordinary matter hides between galaxies as thin, hot gas. When scientists counted up all the atoms predicted by early universe measurements, they found a problem. Stars and visible gas only accounted for a fraction of the expected total. The missing matter was not exotic dark matter. It was ordinary stuff, just hard to see. A leading idea is that many of these atoms live in a warm, hot intergalactic medium, a faint web of gas heated by shocks as galaxies and clusters formed. It is too diffuse to glow brightly and too hot for easy detection in the usual bands. So astronomers look for it by its effect, as it absorbs specific wavelengths from the light of distant quasars, or as it leaves subtle signatures in X-rays. In recent years, the evidence has grown stronger. It is a reminder that emptiness is often only emptiness to our eyes. Between galaxies, the universe still keeps much of its ordinary material. The cosmic web is mapped by gravity, not by light. On the largest scales, matter arranges itself into a vast network of filaments and nodes, with immense voids in between. Some of this structure shines, since galaxies cluster along the filaments. Much of it does not, because the scaffolding includes dark matter and thin gas. To map it, astronomers often rely on gravity's imprint. One of the most powerful techniques is weak gravitational lensing, where the shapes of many distant galaxies are minutely distorted by foreground mass. No single galaxy shape tells you much, but millions together reveal the invisible distribution. Another approach uses how galaxies move within these structures, since their speeds respond to the total mass present. The result is a kind of cosmic cartography, where gravity becomes the ink. It is astonishing that we can draw maps of what we cannot see simply by watching how light is bent and how galaxies drift. The web is a structure you feel, more than one you view. Galaxy clusters reveal mass we cannot see through lensing. A galaxy cluster is a city of galaxies, bound together by gravity on the grandest scales. When a cluster sits between us and more distant galaxies, its mass acts like a lens. Light from the background is stretched into arcs, smeared into elongated shapes, and sometimes split into multiple images of the same object. By measuring these distortions, astronomers can reconstruct where the mass must be, including mass that emits no light. This is not guesswork or artistic inference. It is geometry, built from the way paths curve through space-time. Lensing has also revealed surprising separations between different components in some cluster collisions, where hot gas is slowed by impact, while most mass P10 continues onward. These systems behave like natural laboratories for testing what unseen matter is and how it moves. A cluster can look like a quiet group of galaxies, yet its gravity draws a hidden map across the sky. Some galaxies seem to have too little dark matter. Most galaxies appear to sit inside large halos of unseen mass, which helps explain how they stay together and how they rotate. Then a few odd cases emerged that look different. Their stars move in ways that suggest surprisingly little extra gravity, as if the usual invisible halo is absent or greatly reduced. If these measurements hold up, they raise fascinating questions. Did these galaxies form in an unusual environment, perhaps losing their halo through tidal interactions? Were they born from material torn out during galaxy collisions where dark matter did not follow? Or is there a selection effect that makes us misread their true structure? Each possibility teaches something different. These galaxies are compelling because they test the idea that dark matter is always partnered with visible matter. Nature may be showing us exceptions, and exceptions are often where deeper understanding begins. Other galaxies appear dominated by dark matter from edge to core. Some galaxies are so faint that their starlight is like a thin mist spread across a wide area. Yet their stars orbit faster than their visible mass can explain, even near the center. This suggests that the unseen component outweighs the luminous one almost everywhere. Dwarf spheroidal galaxies around the Milky Way are famous examples. They contain relatively few stars, but those stars move as if held in the grip of a much larger mass. That makes these galaxies valuable targets for dark matter studies, because there is less confusion from bright gas and crowded stellar populations. They are also fragile, easily stirred by nearby giants, which lets us watch how gravity shapes small systems over time. In a way, they are cosmic lanterns with very dim flames, revealing the presence of a much larger, invisible structure. They remind us that brightness is not a reliable guide to what is truly there. Black holes might evaporate through Hawking radiation, but nobody has seen it. In the 1970s, Stephen Hawking realized that black holes are not perfectly black when quantum physics is added to gravity. Empty space near the edge is restless. Particle pairs can momentarily appear, and in rare cases one escapes while the other falls inward. To an outside observer, it looks as if the black hole is slowly leaking energy. That leakage would be unimaginably faint for large black holes, far colder than the natural microwave glow of the universe. So direct detection is out of reach with current technology. Still, the idea has consequences. It links heat, entropy, and gravity in one eerie package, and it suggests that even the darkest objects have a kind of temperature. Researchers also build laboratory analogues, using fluids or optical systems that mimic horizons, to test related physics in controlled settings. The information paradox asks whether black holes destroy history. Imagine tossing a diary into a black hole. The details of every page, every ink stroke, and every fingerprint seem to vanish behind the horizon. If the black hole later evaporates into featureless radiation, where did the diary's information go? Quantum physics insists that information should not be erased, because erasure breaks the rules of how probabilities evolve. General relativity, in its simplest reading, seems to allow it. That collision of principles is the paradox, and it has driven decades of creative thinking. Some proposals say information is somehow encoded on the boundary, like a cosmic accounting system that never forgets. Others suggest it escapes in subtle correlations within the outgoing radiation. There are also ideas involving new physics near horizons that we do not yet understand. This is not a niche puzzle. It reaches into what reality permits and what it forbids. Event horizons are real boundaries, yet they remain unseeable surfaces. An event horizon is not a wall you could bump into. It is a point of no return, defined by the paths that light can take. Outside, a flash can still climb away. Inside, every future path points inward. That makes the boundary strangely absolute, yet impossible to touch in a simple sense. To a distant observer, infilling matter appears to slow and fade, as its light is stretched to longer wavelengths, and its signals arrive more and more delayed. To the falling object, nothing special may happen at the boundary, depending on the black hole's size. This split perspective is part of what makes horizons so unsettling. They are defined by the structure of space-time itself, not by material substance. We infer them through motion, timing, and gravity, rather than by seeing a surface. Supermassive black holes grew early, faster than models expected. Some quasars shine from a time when the universe was still young, and their brightness implies black holes with masses of billions of suns. The mystery is how they got so big so quickly. Growing a black hole by feeding it gas has a natural speed limit, because bright radiation can push incoming matter away. That makes the early giants feel like a race that should be hard to win. One possibility is that the first seeds were already large, formed when huge gas clouds collapsed directly instead of forming normal stars first. Another is that black holes merged frequently in crowded early galaxies, building mass through repeated collisions. There is also the option of brief periods of chaotic feeding, where the usual limits are temporarily exceeded. Each explanation carries different predictions, so every new distant quasar becomes a clue. These objects are not just impressive, they are time capsules for cosmic growth. A black hole can spin so fast it drags space-time. Rotation does not only affect the black hole, it affects space and time around it. In a spinning black hole's neighborhood, space-time is pulled into a whirl, a phenomenon called frame dragging. This creates an ergosphere, where motion becomes compulsory. You can still escape, but you cannot remain still relative to distant stars. The weird consequence is that energy can, in principle, be extracted from the spin, like tapping a flywheel. That idea shows up in models for powerful jets that shoot from galactic centers, where magnetic fields and rotating space may work together to fling material outward at near light speed. Spin also leaves fingerprints in the behavior of hot gas close to the hole, shaping how matter orbits and how radiation varies over time. In the cosmos, rotation is common. In black holes, it becomes a sculptor of space-time itself. Two black holes colliding can ring like a struck bell. When black holes spiral together, the final moment is not a quiet merge. It is a violent reshaping of space-time. After the collision, the newborn black hole is distorted, and it settles by vibrating in specific modes, like a bell that can ring only at certain tones. Those tones are not sound in air. They are gravitational waves, ripples that carry energy away and let the object relax into a stable shape. The remarkable thing is that the frequencies and decay times depend on only a few properties, mainly mass and spin. That makes the ring down a clean test of gravity, because the waveform has a mathematical simplicity that messy astrophysics cannot easily fake. With sensitive detectors, scientists can compare the observed ringing to predictions and look for tiny mismatches. Each merger is both a spectacle and a precise experiment performed by nature. Gravitational waves let us hear events no telescope can see. Light can be blocked, scattered, or simply never produced. Gravitational waves bypass those limitations because they are vibrations of space-time itself. They pass through dust clouds, through stars, and through entire galaxies with barely a change. Detectors on Earth measure them by tracking minuscule shifts in the lengths of long tunnels, changes smaller than an atomic nucleus, caused by a wave washing through. When the first signal was confirmed, it opened a new kind of astronomy. Instead of collecting photons, we listen for the rhythm of orbiting masses, the sudden crash of compact objects, and the long, rising chirp that marks a final spiral. These waves also carry distances in a direct way, since the signal's strength relates to how far it has traveled. With enough detections, the universe becomes a concert hall of hidden catastrophes, and we finally have ears to hear it. Some gravitational wave signals may come from neutron star mergers. Unlike black holes, neutron stars have surfaces, magnetic fields, and layered interiors. When two of them spiral together, the gravitational wave pattern can include extra details because the stars deform under each other's tidal pull. That deformation leaves a subtle imprint on the waveform, offering clues about how stiff or squishy the ultra-dense matter is. Sometimes the merger can also produce light, which turns a gravitational wave detection into a multi-messenger event. In the famous 2017 case, observatories caught both a gravitational signal and a burst of light across many wavelengths, allowing an exquisite cross-check of timing and location. These events are also powerful tools for measuring cosmic expansion, because the gravitational wave provides an independent distance while the host galaxy can provide a redshift. Each neutron star merger is like a coded message from matter pushed to its absolute limits. Neutron star interiors may contain exotic quark matter. A neutron star packs more mass than the Sun into a sphere about the size of a city. Under that pressure, atoms cannot keep their usual structure. Electrons are crushed into protons, forming neutrons, yet even neutrons may not remain intact deep inside. Some theories suggest a core where quarks roam more freely, forming an exotic state of matter unlike anything stable on Earth. Other possibilities include superfluid neutrons, superconducting protons, or strange matter with unfamiliar particles. We cannot drill into a neutron star, so we infer its interior by indirect clues. The maximum mass a neutron star can have before collapsing, the way it cools over time, and the subtle tidal signatures in merger waveforms all help narrow the dumper. Options. Every constraint is precious because it tells us how nature behaves at densities far beyond any laboratory. A neutron star may be a living museum of extreme physics. Magnetars unleash giant flares powered by extreme magnetic fields. Some neutron stars are born with magnetic fields so intense that they make ordinary pulsars look tame. These are magnetars, and their magnetism can store vast energy in the star's crust and surrounding space. When that stressed crust fractures, or when magnetic field lines snap and reconnect, the star can release a sudden flare. For a brief moment, the outburst can outshine everything else in its galaxy at certain energies. A few historic flares have even left detectable fingerprints in Earth's upper atmosphere, despite occurring tens of thousands of light years away. The initial flash can be followed by a fading tail that pulses as the star rotates, like a lighthouse after a thunderclap. Magnetars also produce shorter bursts and persistent X-ray emission, making them a rich, unpredictable class of cosmic object. They are reminders that magnetism, when extreme, becomes a cosmic power source. Pulsars keep time so well they rival atomic clocks. A pulsar is a neutron star that spins with extraordinary steadiness, sweeping a beam across space like a cosmic lighthouse. Each sweep can arrive at Earth with such regularity that astronomers treat it like a natural clock. Some pulsars rotate hundreds of times per second, and their pulses can be predicted far into the future. When the timing shifts by even a tiny amount, it becomes a clue. The star might have glitched, which is a sudden change in spin linked to its crust and interior. Or the pulses might be delayed by gas between stars. There is an even more exciting possibility. A passing gravitational wave would subtly stretch space-time, changing arrival times across a network of pulsars. That is why scientists build pulsar timing arrays. They turn the galaxy into a detector, using ancient spinning stars as precision instruments. Fast radio bursts flash for milliseconds, and their causes vary. Fast radio bursts are brief pulses of radio energy that appear, blaze, and vanish in less than a blink. For a long time, they were mysterious single hits, which made them hard to study. Now we can catch more of them, and we can sometimes pinpoint their host galaxies. They come from far beyond the Milky Way, which means they release an enormous amount of energy in a very short time, at least in radio waves. Some appear in calm galaxies. Others come from regions with active star formation. That variety hints that there may be more than one engine. Magnetars are strong candidates for at least some bursts, since they can produce sudden magnetic upheavals. Yet the details are still unfolding, and new kinds of bursts keep appearing. Each detection is like a postcard from a distant catastrophe, delivered in a single sharp note. Some fast radio bursts repeat, which rules out many explanations. When a burst repeats, it changes the detective story. A one-time explosion like a star being destroyed cannot account for an object that keeps sending flashes months or years apart. Repeaters point toward engines that survive their outbursts, such as highly magnetized neutron stars or compact objects interacting with their surroundings. Some repeaters show complex behavior. They can cluster in storms of activity, then fall silent for long stretches. A few even show periodic cycles of active and quiet phases, which suggests an orbital partner or a wobbling beam. Repetition also lets astronomers localize the source more precisely, because they can wait for another flash, and measure it with multiple instruments. Once a home galaxy is identified, the environment becomes part of the clue, including nearby star-forming regions or dense gas. Repeaters turn the cosmic surprise into a long-running investigation. Gamma-ray bursts can outshine galaxies, yet last minutes. Gamma-ray bursts are among the brightest explosions known, and they announce themselves with high-energy light that can cross the universe. Some are short, lasting less than a couple of seconds. Others are long, lingering for minutes. That division points to different origins. Short bursts are linked to mergers of compact objects, while long bursts are tied to the collapse of massive stars into black holes. The initial flash is only the beginning. Afterward, an afterglow can unfold across X-rays, visible light, and radio as the blast wave plows into surrounding material. By studying that afterglow, astronomers can measure distance, environment, and energy. Gamma-ray bursts also act like backlights. Their light passes through intervening gas, revealing fingerprints of the early universe in absorption lines. For a brief time, a single event can illuminate not only its own death, but the space between galaxies. Ultra-high-energy cosmic rays hit Earth with unknown origins. Sometimes a single particle slams into Earth's atmosphere with the energy of a well-hit tennis ball, concentrated into something smaller than an atom. These are ultra-high-energy cosmic rays, and they are rare. You might wait years for one to strike a square kilometer of sky. When they arrive, they trigger a cascade of secondary particles that spreads outward like an invisible umbrella. Observatories detect these showers with ground arrays and think flashes in the air. The mystery is what can accelerate a particle to such absurd energy. The candidates are dramatic, such as the jets of active galaxies, shockwaves in giant structures, or extreme environments near spinning black holes. Yet magnetic fields bend charged particles, which scrambles their paths and hides their sources. Even composition is debated, since some may be protons, while others may be heavier nuclei. Each event is a clue from an accelerator we have not identified. Neutrinos pass through Earth, carrying messages from violent cosmic engines. Neutrinos are so elusive that trillions pass through your body each second without leaving a trace. They rarely interact with matter, so they can travel straight from their source, crossing galaxies and clouds that would block light. That makes them ideal messengers from extreme places. A neutrino can escape from deep inside an exploding star, or from regions around black holes where dense material would trap photons. Detecting them requires enormous instruments, often built in ice or water, where rare interactions create faint flashes that sensors can catch. When a high-energy neutrino is traced back to a patch of sky, astronomers can look for a counterpart, such as an active galaxy flaring at the same time. This is a new kind of astronomy. It is not about seeing. It is about catching a nearly ghost-like particle and using it to point toward the universe's most powerful engines. The universe should contain a neutrino background we cannot yet detect. Long before atoms formed and the cosmic microwave background was released, the early universe was a hot soup where neutrinos were constantly created, scattered. Then the universe expanded and cooled, and neutrinos stopped interacting much with other matter. They streamed freely through space, forming a cosmic neutrino background that should still fill the universe today. In principle, it is a relic older than the microwave afterglow. In practice, it is extraordinarily hard to detect because these neutrinos are very low energy. They drift through everything almost without notice. Yet their existence is supported indirectly, since neutrinos influence how the early universe expands and how structure grows. Scientists dream of future experiments that could detect the background through subtle effects on radioactive decay or through delicate interactions in advanced detectors. If it were measured directly, it would be like hearing a whisper from an era even earlier than the first light we can see. We still do not know the absolute masses of neutrinos. Neutrinos have mass, but they are so light that measuring their true weights is a major challenge. We know they change type as they travel, a phenomenon called oscillation, and that behavior reveals differences between their masses. It does not reveal the full scale. To find that, scientists use several clever strategies. One is to study beta decay with exquisite precision, watching how energy is shared at the end of the decay and looking for the tiny imprint of neutrino mass. Another is to use the cosmos itself, since massive neutrinos affect how small structures form by smoothing out clumps on certain scales. A third approach searches for a rare process called neutrinoless double beta decay, which would reveal that neutrinos are their own antiparticles and would also purpura. Constrain mass. The answer matters because neutrinos are among the most abundant particles in the universe. Their collective mass shapes cosmic history in subtle ways. Cosmic rays can create showers that reach the ground. A high-energy particle enters the atmosphere, and almost instantly it collides with an air molecule, producing a spray of new particles. Those particles collide again, and the cascade grows. By the time it reaches the ground, the shower can cover a wide area, with muons and other particles arriving in a brief burst. You are not usually aware of it, but detectors can count these arrivals and reconstruct the original cosmic ray's energy and direction. Some showers are detected by arrays of sensors spread across deserts or high plains. Others are inferred through faint ultraviolet light, produced when the cascade excites nitrogen in the air. This technique turns the atmosphere into part of the instrument. It also reveals the universe as an active place. Space is not empty and calm. It is filled with particles in motion, many launched by violent astrophysical processes and delivered to Earth as a constant, invisible rain. Space is filled with plasma, and its behavior is still tricky. Plasma is a state of matter where atoms are stripped into charged particles, and it dominates the visible universe. Stars are plasma. The solar wind is plasma. Many nebulae in the space between stars contain plasma too. Because the particles are charged, electric and magnetic fields can steer them, twist them, and store energy within them. That leads to behaviors that are unfamiliar if you only think in terms of ordinary gases. Plasmas can form filaments, double layers, and sudden eruptions when magnetic fields reconnect. They can also generate waves that move energy over great distances. Understanding plasma is not only an academic pursuit. It affects how stars shed mass, how planets are battered by space weather, and how jets and accretion disks behave around compact objects. It also shapes technology, from fusion research to satellite safety. In many corners of the cosmos, magnetism and plasma choreograph the action together. The solar corona is hotter than the surface, and that is odd. If you move away from a campfire, you expect the air to cool. The sun does the opposite. Its visible surface is hot, yet the outer atmosphere above it reaches temperatures of millions of degrees. That should not happen if heat simply leaks outward. Something must be pumping energy into the corona. The leading suspects are magnetic. The sun's tangled field can braid, snap, and reconnect, releasing stored energy in sudden bursts. There are also waves that travel through solar plasma, carrying energy upward like vibrations along a rope. Spacecraft that fly close to the sun have begun sampling this region directly, measuring particles and fields where the heating happens. Even so, the full recipe is still debated. This mystery matters because the corona is the source of the solar wind, and that wind shapes the environment of every planet. The Sun's magnetic field flips roughly every 11 years. The Sun is not a solid ball. Its equator rotates faster than its poles, and that differential rotation stretches magnetic field lines like taffy. Deep inside, churning plasma and rotation act together as a dynamo, building and rearranging magnetism over time. As the cycle progresses, sunspots appearing bands drift toward the equator and then fade. Near the peak, the global magnetic pattern becomes complex, and the Sun's north and south magnetic poles swap. After the reversal, the cycle begins again with the new polarity. This flip is more than a curiosity. It changes how magnetic storms propagate through the solar system, and it influences the intensity of space weather near Earth. Scientists track the cycle with satellites that watch the Sun's surface and atmosphere, because understanding the rhythm helps forecast the moments when the Sun is most restless. Solar storms can reshape Earth's skies with auroras. When the Sun throws out a cloud of charged particles and magnetic fields, it can sweep across the solar system like a fast-moving weather front. If it arrives at Earth, our magnetic field deflects most of it, yet some energy funnels toward the polar regions. There, particles slam into the upper atmosphere and excite oxygen and nitrogen. As those atoms relax, they emit light, painting curtains, arcs, and rippling bands across the night. The colors are not decorative choices. Green often comes from oxygen at certain heights, while reds and purples can hint at different altitudes and energies. During especially strong storms, auroras can drift far from the poles, startling people who have never seen them before. These events are beautiful, but they are also a reminder that Earth lives inside the Sun's influence, not apart from it. We do not fully understand how stars explode as supernovas. A massive star ends its life when it can no longer support itself against gravity. Its core collapses in a fraction of a second, and a shockwave forms. In early computer models, that shock often stalls, as if the star refuses to finish the job. Yet in the real universe, many stars do explode, and the blast can shine brighter than an entire galaxy for a short time. The missing ingredient seems to involve neutrinos, turbulence, and complex flows inside the collapsing star. Neutrinos carry away enormous energy, and some of that energy may help revive the stalled shock. Rotation and magnetic fields can also shape the explosion, sometimes producing jets. The details matter because the blast determines what elements are scattered into space and what remnant is left behind. A supernova is both a death and a cosmic construction project, and the engine is still being solved. Some stars collapse directly into black holes with little warning. Not every massive star ends with a brilliant farewell. In some cases, the core collapse may fail to launch a successful explosion. The star can simply fold inward, and a black hole forms while the outer layers fall after it. From far away, the star might dim and vanish, as if a light was quietly switched off. Astronomers have tried to catch these events by watching nearby galaxies for massive stars that disappear without a supernova. The searches are difficult because you need years of monitoring and very clear images. Still, the idea fits a tantalizing clue. We see fewer supernovas than expected from the number of massive stars that should die. Direct collapse could help close that gap. It would also explain how some black holes are born heavy without shedding much mass in an explosion. Sometimes the universe may choose silence over fireworks. A supernova makes heavy elements, including much of the gold on Earth. A massive star spends its life forging elements in layers, turning hydrogen into helium, then building up to carbon, oxygen, silicon, and eventually iron. Iron is a dead end for ordinary fusion, so when collapse comes, the star's internal chemistry is already rich. In the violence of the explosion, intense heat and floods of particles can create new isotopes and push atoms into heavier forms. The blast then sprays those elements into space, seeding future clouds that become stars and planets. Some of the heaviest elements, including a portion of Earth's gold, likely require especially neutron-rich conditions that may occur in certain supernova environments. The exact contributions are still debated, yet the larger truth is solid. The calcium in your bones and the iron in your blood were made in stellar interiors, then delivered across space by ancient explosions. A supernova is a cosmic delivery system, scattering the ingredients for future worlds. Neutron star mergers also forge heavy elements, but proportions are debated. When two neutron stars collide, they fling out extremely dense matter that rapidly decompresses. In that moment, atomic nuclei can capture neutrons faster than they can decay, building very heavy elements in a chain reaction called the rapid process. The radioactive debris glows as it decays, producing a kilonova, which can shine in optical and infrared light for days. That glow carries fingerprints of freshly made elements, and it provides some of the clearest evidence that mergers are major factories for the heaviest nuclei. The open question is how much of the cosmic inventory they supply. Mergers are rare compared with supernovas, yet they produce a lot per event. Their rate may also have changed over cosmic time. Some chemical patterns in old stars suggest multiple sources. So the debate continues, and it is a thrilling one. It asks which catastrophes paid the bill for the rarest metals in the universe. White dwarfs can steal matter until they detonate as standard candles. A white dwarf is the dense core left behind when a sun-like star finishes its life. In a close binary, it can pull gas from a companion star. As that stolen material piles up, pressure and temperature rise on the dwarf's surface. Under the wrong conditions, the buildup can ignite in a runaway thermonuclear blaze. The star is not merely burning fuel. It is unbinding itself. The result is a Type 1a supernova, an explosion bright enough to be seen across huge distances. Because many of these events reach similar peak brightness, astronomers use them to measure the scale of the expanding universe. That use is powerful, yet it depends on understanding the details of how the explosion starts. Does the white dwarf reach a critical mass? Or can it detonate earlier through surface ignition and shock? Different paths can produce slightly different brightness. This is why these explosions are both tools and puzzles, lighting up the sky and testing our assumptions at once. Some standard supernovas show surprising diversity that complicates distances. Type 1 supernovas became famous because they appeared to behave like reliable beacons. Over time, deeper surveys revealed that they are not perfectly identical. Their brightness and color can vary with the properties of their host galaxies, their local environments, and the exact way the explosion begins. Dust can also redden and dim the light, and dust behaves differently from place to place. Astronomers handle this by using careful calibrations, comparing light curve shapes, colors, and spectra to standardize each event. The method works well, yet the remaining scatter matters because these supernovas underpin some of our most important measurements, including the rate of cosmic bar. Expansion. Diversity is not a failure. It is information. Each variation is a clue about the progenitor system, the ignition mechanism, and the physics of nuclear burning under extreme conditions. The better we understand the diversity, the more trustworthy the cosmic yardstick becomes. The heaviest elements require rare events we are still counting. Elements like uranium and thorium are not produced in ordinary stellar fusion. They demand environments with huge neutron supplies and violent energy, where nuclei can grow quickly and then settle through radioactive decay. We know some candidate sites, yet we are still tallying their contributions. Neutron star mergers are one strong source, but their frequency over the history of the universe is uncertain. Certain unusual stellar explosions may also contribute, including events driven by rapid rotation and strong magnetic fields, which can create neutron-rich outflows. The evidence is written in the chemistry of very old stars. Some contain unexpectedly high amounts of rapid process elements, while others contain almost none. That patchiness suggests that the enrichment happened in rare, localized bursts. Each time we measure stellar abundances in the Milky Way's oldest populations, we are reading a forensic record of ancient catastrophes. The heaviest elements are not common because the events that make them are not common. That rarity is part of their story. Many exoplanets orbit so close they are slowly being stripped away. Some planets skim their stars so tightly that they live inside a storm of radiation and charged particles. The star's ultraviolet light can heat the upper atmosphere until it swells outward. Then the stellar wind carries that gas away like smoke in a strong breeze. Astronomers can sometimes watch the loss in real time. In certain hot planets, hydrogen leaves such a large cloud, but it changes how the starlight looks during a transit. These worlds are not stable in the way Earth feels stable. Their size, density, and chemistry can evolve over millions of years, which is quick by cosmic standards. A planet can begin as puffy and end as compact, or lose key molecules that once shaped its climate. Each evaporating world is a natural experiment, showing how harsh light can sculpt a planet's fate. Some exoplanets are tidally locked, with permanent day and night. When a planet orbits close to its star, gravity can force it into a spin state, where one side always faces the light. That creates a permanent D side and a permanent night side, and the boundary between them becomes the most important region on the world. If the atmosphere is thick enough, winds can carry heat around, softening the temperature contrast. If the air is thin, the day side can become blistering while the night side freezes into darkness. Scientists model these planets with climate simulations that include jet streams, cloud formation, and even the possibility of dayside storms that never end. Some models predict a bright reflective cloud deck on the hot side that changes the planet's observed brightness. Tidally locked worlds also challenge the usual idea of habitability. Life, if it exists, might favor a ring of mild conditions near the terminator, where sunrise and sunset never move. Atmospheric escape can turn a Neptune-like planet into a bare core. Some planets seem to sit in an in-between category. They are larger than Earth, smaller than Neptune, and they often appear in tight orbits. One explanation is that many began with thick envelopes of hydrogen and helium, then lost them over time. A strong star can heat the upper layers until they stream away, especially in young systems where stars are more active. As the gas escapes, the planet shrinks and its density rises. What remains may be a rocky or water-rich core that once hid under a giant atmosphere. This process helps explain why astronomers see a gap in planet sizes, with fewer worlds in certain radius ranges. It also means that the planet you detect today might not resemble the planet that formed. Each stripped core is a clue to the early history of its star and to how vulnerable atmospheres can be. Water worlds may exist with oceans far deeper than Earth's. Imagine a planet where water is not a surface feature, but the dominant geology. Some models allow worlds with global oceans hundreds of kilometers deep, far beyond any trench on Earth. At those pressures, water behaves differently. Deep down, It can form exotic high-pressure ice that is still solid even at warm temperatures. That creates a strange layered planet. You might have ocean on top, then a thick shell of dense ice, then rock beneath. This matters for life because contact between water and rock can drive chemistry, yet a high-pressure ice layer could cut off that interaction. Scientists look for hints of such planets through density measurements, since water-rich worlds are often less dense than rocky ones of the same size. A deep ocean also changes climate. It can store heat, circulate slowly, and blur the line between atmosphere and sea. Water worlds expand the idea of what a planet can be and what life would need. A planet might rain iron depending on its chemistry and heat. On some ultra-hot giant planets, temperatures can soar high enough to vaporize metals. That means materials we think of as solid can exist as gas in the upper atmosphere. As winds carry that vapor to cooler regions, it can condense into droplets and fall, which makes the phrase iron rain more than a metaphor. Astronomers cannot watch individual raindrops, but they can detect the chemical fingerprints of metals in the planet's atmosphere by studying how starlight filters through during a transit. The spectra can show sodium, potassium, and even hints of iron and other heavy elements, depending on the world. These planets also have fierce winds driven by the contrast between hot and cool regions, which can redistribute vapor before it condenses. Weather on such a planet is not about water. It is about rock and metal cycling through the sky and falling back down in an alien storm. Rogue planets wander without stars, warmed only by internal heat. Not every planet stays loyal to a star. During the chaotic early years of a planetary system, close encounters can fling a world outward until it escapes entirely. The result is a rogue planet, drifting through interstellar space with no sunrise and no year. You might think such a world would be an instant ice ball, yet it can still carry heat. Radioactive elements in the interior can keep a core warm, and if the planet is large enough, leftover heat from formation can linger for a long time. Some scientists even consider the possibility of subsurface oceans beneath thick ice, insulated like a thermos, although this depends on composition and size. Detecting rogues is difficult, since they do not shine like stars. One method is microlensing, where a passing planet bends background starlight and briefly brightens it. Each detection suggests that the galaxy may be filled with dark, wandering worlds. Some moons may hide oceans beneath ice, and we are searching. In the outer solar system, sunlight is weak, yet several moons show signs of internal activity. The secret is tidal heating. As a moon orbits a giant planet, gravity flexes it over and over, kneading the interior and generating heat. That heat can maintain a liquid ocean beneath an icy shell. This idea changes what it means to be a potentially habitable place. You do not need to orbit in a narrow band around a star if you have energy from tides and chemistry from rock and water. Scientists look for indirect clues. A magnetometer can detect a conductive salty ocean by how it responds to changing magnetic fields. Surface cracks and chaotic terrain can hint at motion below. Plumes, if present, can deliver subsurface material into space. Each of these signs is a piece of a larger puzzle. Hidden oceans are not science fiction anymore. They are targets. Europa's surface fractures hint at an active ocean below. Europa looks like a bright ice world, etched with long lines that crisscross its surface. Those lines are more than decoration. They suggest that the ice shell has been pulled, broken, and shifted by stresses over time. Some regions appear jumbled, as if blocks of ice have rotated and refrozen in place. That kind of terrain is hard to explain without something mobile beneath. such as liquid water or slushy ice. Europa also sits inside Jupiter's powerful magnetic environment, and measurements are consistent with a conductive layer that could be a salty ocean. If an ocean exists, it may contact a rocky seafloor, which raises exciting possibilities for chemistry. The challenge is access. The ocean is hidden beneath ice that could be kilometers thick. Still, the surface is speaking in patterns. Every fracture is a record of forces at work and a clue to a sea that might be moving in darkness. Enceladus sprays plumes that reveal ocean chemistry directly. Enceladus is small, yet it behaves like a world with plumbing. Near its south pole, jets of icy particles and vapor shoot into space from long cracks in the ice. Those plumes form a broad cloud that feeds Saturn's E-ring, and they offer a rare gift. They bring subsurface material to an altitude where a spacecraft can sample it. Measurements have detected water vapor, salts, and organic molecules in the plume material, which strongly supports the presence of a liquid ocean beneath the ice. There is also evidence for tiny silica grains, which can form when hot water interacts with rock, suggesting hydrothermal activity on the seafloor. That combination, water, rock, and energy, is the trio that makes astrobiologists pay attention. Enceladus turns an inaccessible ocean into something you can taste with instruments, and it makes the search for life feel less distant. Titan has lakes of methane, shaping shores like Earth's. Titan is wrapped in a thick orange haze, and beneath it lies a landscape that feels strangely familiar. There are dunes, channels, and smooth basins that hold liquid. The twist is that the liquid is not water. It is methane and ethane, stable at Titan's frigid temperatures. Titan even has a kind of weather cycle. Methane can evaporate, form clouds, and fall as rain, carving river-like features that drain into polar seas. Radar mapping has revealed shorelines and lake surfaces that reflect signals like calm water does on Earth. This makes Titan a natural laboratory for understanding how landscapes evolve when the working fluid changes. It also offers a chemistry playground. Sunlight and energetic particles can break apart methane in the upper atmosphere, creating complex organic compounds that settle onto the surface. Titan shows that familiar processes, erosion, rainfall, and shoreline growth can occur in utterly unfamiliar chemistry. Mars releases trace methane sometimes, and the source is unclear. Orbiters and rovers have reported small, sometimes fleeting hints of methane in the Martian air. On Earth, methane often points to life or geology, so even a trace on Mars draws intense attention. The trouble is that the signal can appear and disappear, and different instruments do not always agree on the timing or the amount. If the methane is real, it could come from rock chemistry underground, where water and certain minerals react to produce gas. It could also be released from ancient reservoirs, trapped in ice or within porous rock, and then vented by seasonal temperature changes. A more exotic possibility is active microbes, although no evidence confirms that. There is also a hard puzzle on the other side. Sunlight and chemistry should break methane down, so something must replenish it if it persists at all. Each detection is like a whisper from below the surface, inviting us to keep listening. Venus may have unknown chemistry high in its clouds. Venus is often called Earth's twin, yet its atmosphere is a crushing furnace at the surface. High above that inferno, the clouds form a different realm, with temperatures and pressures that are far less extreme. Those clouds are dominated by sulfuric acid droplets, and they host a complicated mix of gases that sunlight constantly reshapes. Spectral observations have raised puzzles about certain absorption features and trace compounds, and interpretations have been debated fiercely. Some proposed signatures have been challenged, while alternative explanations have multiplied. That is part of what makes Venus so captivating right now. The planet is close, bright, and still full of chemical surprises. Future missions aim to sample the air directly, measure isotopes, and map the dynamics of the cloud layers. The goal is not only to solve one controversial signal, it is to understand an entire atmospheric laboratory that has been running for billions of years. The asteroid belt holds relics from planet building that never finished. Between Mars and Jupiter lies a region filled with rocky bodies that never became a planet. Early in the solar system, countless fragments orbited there, colliding, sticking, and sometimes shattering again. Jupiter's gravity played a disruptive role, stirring the region and increasing impact speeds until growth became difficult. What remains is a fossil collection of building blocks. Some asteroids are primitive and carbon-rich, preserving ancient chemistry. Others are metal-heavy, likely pieces of larger bodies that differentiated into cores and mantles before being broken apart. Meteorites that fall on Earth often come from this region, and their textures record heating, impacts, and the slow alteration by water in the early solar system. Visiting asteroids up close has shown landscapes shaped by rubble, boulders, and surprisingly low gravity. The belt is not a leftover junk drawer. It is a museum of how planets try to form and how they can fail. Comets preserve ancient ices from the solar system's birth. A comet is often described as a dirty snowball, but that simple phrase hides a deep time capsule. Many comets spent most of their existence far from the Sun, in cold storage where ices and dust changed very little. When a comet dives inward, sunlight warms it and releases gas and dust, building a glowing coma and a tail that can stretch for millions of kilometers. That material is not just pretty. It contains water ice, carbon-bearing compounds, and other volatiles that were present when the planets were assembling. Space missions have sampled comet dust, measured the composition of comet atmospheres, and even photographed jets erupting from shadowed cliffs. The ratios of different molecules can hint at where the comet formed and how the early disk was layered. Each return of a comet is a brief thaw of ancient material, letting us study ingredients that existed before Earth was fully built. Interstellar objects can pass through our system, bringing unknown histories. Every so often, the solar system gets a visitor that was not born here. These objects arrive on paths that do not loop around the Sun, which means they are passing through from the wider galaxy. Their speed and trajectory reveal that they belong to no familiar family of comets or asteroids. In a sense, they are free samples of other planetary systems, delivered without needing a starship. Some look dusty and comet-like. Others appear more inert, with unusual brightness changes that hint at odd shapes or tumbling rotations. Because they move fast, we get only a short time to observe them, which makes rapid response essential. Wide field surveys are improving, and that raises an exciting possibility. If we find more visitors, we can start comparing them, building a census of alien debris. Each one is a fragment of another system's story, shaped by a different star, then flung into interstellar night. Oumuamua's strange acceleration sparked debates about its nature. After the first known interstellar visitor was discovered, astronomers tracked its motion with extreme care. Its path did not match gravity alone. It seemed to gain a small extra push as it left the Sun, a behavior often explained by outgassing, where escaping vapor acts like a gentle thruster. The puzzle was that telescopes did not clearly see the expected dust cloud that usually accompanies such activity. That opened a storm of interpretations. Some researchers suggested a very faint kind of outgassing, perhaps hydrogen, perhaps water released in an unusual way, that could produce thrust without obvious dust. Others explored the idea that radiation pressure from sunlight could nudge a thin, low-density object. A few speculations went far beyond natural explanations, which drew attention but not consensus. What remained solid is the lesson. One brief visitor exposed how limited our observations can be and how quickly mystery returns when the data window is short. Meteorites contain older grains than the Sun itself. Hidden inside some meteorites are tiny mineral grains that formed before our solar system existed. These pre-solar grains condensed in the outflows of dying stars or in the debris of stellar explosions, then drifted through interstellar space until they were swept into the cloud that became the Sun and planets. They are microscopic, yet they carry unmistakable signatures in their isotopes, ratios that do not match anything made in the solar system. Finding them is painstaking. Scientists dissolve away most of the meteorite and isolate the resistant grains, then analyze them atom by atom. The payoff is extraordinary. Each grain is a direct physical sample of another star, older than Earth, older than the Sun, older than the planets. In most astronomy, we infer stellar history from light. Here, you can hold it in your hand. Meteorites are not only rocks from space. They are archives of stellar neighborhoods that existed long before our own. Some meteorites carry amino acids, raising questions about life's ingredients. Amino acids are basic building blocks of proteins, and several types have been found in certain carbon-rich meteorites. This does not mean life arrived ready-made. It means complex organic chemistry can happen in space, inside small bodies where ice, minerals, and energy sources interact over long periods. Some of these molecules may have formed in the early solar system, while others may have formed even earlier in interstellar clouds. Scientists test for contamination carefully, since Earth is full of organics that can confuse the picture. When the evidence holds up, it suggests that prebiotic ingredients may be widespread, not rare. Impacts in the early history of Earth could have delivered a mixture of water, minerals, and organics, adding to what Earth was already making on its own. The bigger question is still open. Are the ingredients common while the recipe for life is hard? Or are both common, and we are just beginning to notice? Lunar samples record impacts that may have reshaped early Earth. The Moon has no global oceans and no active plate tectonics to erase its ancient scars. That makes it an unusually honest historian. Rocks brought back by Apollo missions and samples from lunar meteorites contain records of intense bombardment early in solar system history. By dating these materials, scientists can reconstruct when major impacts occurred and how frequently they happened. That matters for Earth, because Earth would have been hit too, often with even larger consequences due to its stronger gravity. Giant impact can melt crust, vaporize oceans, and reset surface environments. They can also deliver material and energy that changes a planet's chemistry. The lunar record is not a perfect diary, and interpretations have shifted as measurements improve. Still, it remains one of our best guides to a time on Earth that has largely been erased. When you hold a lunar rock, you are holding a page from the early solar system written in shock and heat. Earth's water may have arrived from multiple sources, not one. Earth formed in a region that was warm enough to make water delivery complicated. Early heat could drive off volatiles, yet the planet ended up with oceans. Evidence suggests the answer may be a blend of contributions over time. Some water likely came from the planet's own building blocks, locked in minerals that later released it through volcanism and degassing. Additional water may have been delivered by impacts from small bodies that formed farther from the Sun, where ice was more stable. Different sources carry different isotopic fingerprints, especially in the ratio of heavy hydrogen to ordinary hydrogen. Measurements do not point cleanly to a single origin story, which is why a mixed model has grown more popular. The implication is beautiful. Earth's oceans may be a mosaic assembled through growth, geology, and chance deliveries, rather than a single lucky gift. Water on Earth is not only a feature, it is a history written in chemistry. The Fermi paradox asks why we see no alien signals. If life can arise on many worlds, and if technology is not a once-in-a-universe accident, then the galaxy ought to feel busy. There are billions of stars, and the Milky Way is old enough for civilizations to rise, spread, and leave traces. Yet the sky is silent. That mismatch is the Fermi paradox, and it is not a single question. It is a whole cluster of possibilities. Maybe intelligent life is rare. Maybe it does not last long. Maybe advanced societies choose not to broadcast, or they communicate in ways we have not learned to detect. There is also the unsettling option that evidence is present, but we are not looking with the right tools or the right patience. The paradox is powerful because it turns our own existence into a data point, and it challenges us to explain the quiet without assuming we are special. The wow signal remains intriguing, yet it never repeated. In the late 1970s, a radio telescope scanning the sky recorded a narrowband signal that stood out from the background like a single clear note. It lasted less than 2 minutes, which fit the timescale of a telescope beam passing over a source as Earth rotated. The signal seemed to come from a region near the constellation Sagittarius, and it was strong enough to make a researcher scribble "wow" in the margin. The mystery is not only what it was, it is that it did not come back. Follow-up searches aimed at the same area found nothing comparable. That leaves several possibilities. It could have been a rare natural event. It could have been human interference that fooled the system. Or it could have been something truly distant and intentional that happened only once, or only rarely. One brief spike created decades of curiosity, because it sits right on the line between mundane and astonishing. Life might be common, while intelligent civilizations are rare. Microbes appeared on Earth surprisingly early, at least by what our rocks suggest. Complex life, however, took much longer to evolve, and intelligence that builds radios arrived very late in Earth's story. That pattern inspires an idea. Perhaps simple life is easy to start, yet the path to advanced technology is full of bottlenecks. You might need stable climates for long stretches. You might need the right mix of continents and oceans. You might need plate tectonics to recycle nutrients, or a large moon to steady a planet's tilt. You might need lucky evolutionary innovations that are hard to repeat. None of these are proven requirements. They are hypotheses that try to explain why biology could be widespread, while cosmic conversation remains rare. The thought is both hopeful and humbling. The universe might be alive in many places, yet still mostly quiet in the ways we can notice. Technosignature searches now look beyond radio into infrared waste heat. Radio is a natural starting point for searching, because it can travel far and it is easy to generate. Yet it is not the only clue a technological society might leave behind. Any civilization that uses large amounts of energy must eventually dump that energy as heat. On a planetary scale, that could slightly change the infrared glow of a world. On a stellar scale, ambitious engineering could alter how a star's light is absorbed and re-emitted. Astronomers can look for unusual infrared excesses, odd light curves, or structures that do not match known natural patterns. These searches must be cautious, because dust and ordinary astrophysics can mimic strange signals. Still, broadening the hunt matters. It reduces the chance that we miss evidence simply because we expected it to look like a radio broadcast. Technosignatures are about behavior, not biology. They invite us to imagine many kinds of technology and then ask what fingerprints physics would force them to leave. The Drake equation is simple, but every term is uncertain. The Drake equation looks like a tidy way to estimate how many communicating civilizations might exist. It multiplies factors, such as how often stars form, how many have planets, and how many of those planets could support life. Then, it adds the hardest parts. How often does life actually appear? How often does intelligence arise? How long do technological societies remain detectable? Each term is a doorway into a different science, from astronomy to geology to evolution to sociology. Some of the early terms are improving quickly, because exoplanet surveys have shown that planets are common. The later terms remain wide open, because we have only one known example of life, and one known example of a radio-capable species. The equation is valuable anyway. It forces us to name our assumptions, and it shows exactly where our ignorance lives. It is not a calculator that gives answers. It is a map of questions. We do not know how often planets become truly habitable. A planet can sit in the right temperature zone and still be hostile. It might lose its atmosphere to stellar winds. It might start with too little water or end up locked under global ice. It might suffer runaway greenhouse heating, or it might have a surface sterilized by extreme radiation. Habitability is not a single dial. It is a network of processes that must work together for long periods. Atmospheres must be retained and renewed. Chemistry must cycle key elements. A star's activity must be survivable, not only on rare bad days, but over eons. Even a planet's interior matters, because volcanic outgassing can rebuild air after loss, while magnetic fields can help shield it. When astronomers say a world is potentially habitable, it usually means only that liquid water could exist somewhere on the surface. The deeper question is persistence. How many worlds stay friendly long enough for life to gain a foothold and diversify? We are only beginning to learn. The origin of life might require rare chemistry, or it might not. We still do not know which step is the hardest. Is it easy to go from simple molecules to self-copying chemistry, given water, energy, and time? Or is that transition so unlikely that it almost never happens? Earth cannot answer that alone, because we do not know how many failed attempts happened here before success, or what environments mattered most. Researchers explore many pathways. Some focus on hydrothermal vents, where mineral-rich fluids meet cold ocean water and create natural chemical gradients. Others look to shallow pools, where cycles of drying and wetting could concentrate molecules and encourage complex reactions. There are also experiments with ice, with clays, and with ultraviolet light as a driver. Each approach can produce promising pieces, like building blocks of RNA or simple membranes. The mystery is how those pieces assemble into a system that can evolve. If the transition is easy, the galaxy could be full of life. If it is hard, we might be a rare chemical miracle. Some scientists consider shadow biospheres with unfamiliar biochemistry. On Earth, almost all known life shares the same basic chemistry: DNA or RNA for information, proteins for function, and familiar metabolic pathways. The shadow biosphere idea asks a daring question. What if Earth also hosts life that does not use the standard toolkit, and we have simply overlooked it because our tests are designed to detect what we already know? Such organisms might use different building blocks, different solvents, or different information molecules. They might live in extreme niches where competition with familiar microbes is limited. Searching for this is difficult, because you must avoid circular logic. If you use the usual genetic stains and culture methods, you will preferentially find ordinary life. Instead, Researchers look for anomalies, cells that do not behave like expected biology, or chemical signatures that suggest alternative metabolisms. No confirmed shadow biosphere has been found, but the concept is valuable. It reminds us that discovery is shaped by the assumptions built into our instruments, and that unfamiliar life could be invisible to familiar eyes. Panspermia suggests life can travel, but evidence is still thin. Panspermia is the idea that life, or its precursors, can move between worlds. It might ride inside rocks blasted off a planet by impacts, then drift through space and land elsewhere. Some hardy microbes can survive extremes of cold, vacuum, and radiation for a time, which keeps the idea from being instantly dismissed. There are also organic molecules in space, including in comets and meteorites, which shows that some ingredients can travel widely. The hard part is proving that living systems can survive the full journey, and proving that they have. Even if life can travel, panspermia does not solve the deepest problem. It moves the origin to another place. Still, it could change how common life becomes. If one planet develops life, and if exchange of material is possible, then nearby worlds might be seeded more easily than starting from scratch. The idea is a bridge between biology and celestial mechanics, and it keeps the search for life connected to the movement of worlds. Extinctions could reset complex life repeatedly on many worlds. Complex ecosystems are fragile in a way that microbes are not. A planet can host simple life for eons, yet struggle to maintain stable environments where large, diverse organisms can thrive. Impacts, supervolcano episodes, nearby stellar flares, and long-term climate shifts can all cause mass extinctions. On Earth, life recovered, but recovery took time, and the winners were not guaranteed. On another world, repeated catastrophes could keep knocking complexity back to the starting line. Even if intelligence is possible, it may require long stretches of relative stability, plus evolutionary luck. This idea offers one path through the cosmic silence. The universe might be full of living planets, yet few may reach the stage where technology can arise and persist. Extinctions also complicate our search, because a world could have hosted advanced life in the distant past and now appear quiet. The night sky might not be empty of stories. It might be full of stories that ended. The Milky Way is eating smaller galaxies, and it is still happening. Our galaxy is not a closed island of stars. It grows by gravity, and gravity is patient. Small companion galaxies drift too close, then tidal forces begin to stretch them like taffy. Stars are pulled into long arcs, and dark matter is stripped even more easily. Over time, the visitor dissolves into the Milky Way, adding new stars to the halo and stirring the motions of older ones. This is not only ancient history. Astronomers are watching ongoing interactions right now, including systems that are visibly being torn apart. The evidence is written in star motions, chemical fingerprints, and faint structures that wrap around the sky. Every time the Milky Way absorbs a smaller neighbor, it changes its own shape a little. The galaxy you see tonight is the result of many quiet meals. Stellar streams are fossil trails from galaxies torn apart. If you could turn up the contrast on the night sky, you would see faint ribbons of stars looping around the Milky Way. These are stellar streams, and they form when a star cluster or small galaxy is pulled apart by tidal forces. The stars do not scatter randomly. They keep moving on similar orbits, so they trace out graceful paths that can persist for billions of years. That makes them valuable. A stream is like a line of footprints, showing where the disrupted object traveled and how the Milky Way's gravity shaped it. Streams also act like probes of dark matter, because their thickness and clumpiness can reveal invisible lumps that disturb their paths. Astronomers map them using huge surveys that measure positions, brightness, chemistry, and motion. When a new stream is discovered, it is not just pretty structure. It is a preserved record of a cosmic encounter, still drifting overhead. The center of our galaxy hides a black hole we can track. At the Milky Way's core, dust blocks visible light and hides the crowded star field behind it. Infrared telescopes can pierce that veil, and they reveal stars moving at astonishing speeds in tight orbits around an unseen point. By watching those orbits over many years, astronomers can measure the mass of the central object with remarkable confidence. The result is a supermassive black hole, known as Sagittarius A star, with a mass of millions of suns. One star in particular has traced a full orbit in a human lifetime, swinging close and then racing away again. These measurements are like celestial clockwork, and they let us test gravity in a strong field environment. The galactic center is not quiet. It is a laboratory where invisible mass announces itself through motion, and where the heart of the Milky Way becomes something we can measure, not just imagine. Andromeda is approaching, and a future merger is expected. Andromeda is the nearest large galaxy to the Milky Way, and it is moving toward us. Over billions of years, gravity will pull the two spirals into a slow dance. First, their outer halos will interact. Then their disks will pass through each other, distorting into long tidal tails. Stars will mostly avoid direct collisions because space is vast, yet their orbits will be scrambled by changing gravity. Gas clouds, however, can collide and compress, which can trigger waves of star formation. Eventually, the galaxies will settle into a single larger system with a new shape. The night sky from Earth will look dramatically different during that era, with Andromeda growing larger and more complex over time. This is not a sudden crash. It is a drawn-out transformation that will unfold across cosmic timescales. A merger is one of the ways galaxies evolve, and we are part of one that is already on its way. Galaxies can stop forming stars, and the shutdown mechanism varies. Star formation requires cold gas. It also requires that the gas stay cold long enough to collapse into dense clouds. Many galaxies lose that ability, and they become quiet systems filled with older stars. The reasons differ. Some galaxies fall into clusters where hot intracluster gas can strip away their own gas like a headwind. Others exhaust their supply, turning gas into stars until little remains. In some cases, gas is heated and kept from cooling, which prevents new clouds from forming even if material is still present. Mergers can also play a role, stirring gas in ways that can trigger a burst, followed by depletion. The result is a population of galaxies that are still luminous, yet no longer building new suns. This transformation shapes the colors of galaxies across the universe, since young stars shine blue while older populations glow redder. When a galaxy shuts down, it changes its future for billions of years. Supermassive black holes influence galaxy growth through energetic feedback. A feeding supermassive black hole can look like a quasar, and it can release more power than all the stars in its galaxy combined. That energy does not stay near the center. It can drive winds that push gas outward, and it can launch jets that punch through the surrounding medium. Both effects can change how much cold gas remains available to form stars. In some situations, feedback appears to quench star formation by heating gas or expelling it from the galaxy. In other situations, the same energy can compress gas in certain regions and trigger new star formation, at least locally. This is why feedback is so important. It links the smallest scales near a black hole to the largest scales of galaxy evolution. Observations show correlations between black hole mass and properties of the host galaxy, which hints at a long coevolution. The black hole is not just a passenger. It can be a regulator, shaping how a galaxy grows up. Cosmic voids are enormous, and their origins test our models. Between the bright filaments of the cosmic web lie regions with very few galaxies. These are cosmic voids, and some are hundreds of millions of light-years across. They are not completely empty. They contain thin gas and dark matter, yet their density is lower than average. Voids form because gravity pulls matter into denser regions, leaving underdense regions to expand and become emptier over time. That makes them sensitive tests of cosmology. The way voids grow depends on dark energy, on the nature of gravity, and on how matter clusters. Astronomers study voids using galaxy surveys and statistical methods, looking for subtle patterns in their shapes and their distribution. Voids can also affect the light that passes through them, leaving faint imprints on background signals. In a universe shaped by gravity, emptiness becomes informative. A void is not nothing. It is a measurable outcome of how structure forms. The Great Attractor tugs galaxies, yet its full structure is hard to map. When astronomers measure the motions of galaxies near us, they find a large-scale flow. Many galaxies seem to be moving toward a broad region of space, as if drawn by a hidden concentration of mass. This is often called the Great Attractor. The challenge is that the region lies partly behind the plane of the Milky Way, where dust and dense star fields obscure our view in visible light. That makes mapping difficult, like trying to chart mountains through fog. Observations in infrared and radio help, because they can see through the dust more effectively. Surveys have revealed clusters and superclusters in that direction, suggesting that the pull comes from a complex web of structures rather than a single object. The Great Attractor is a reminder that even our local universe is not fully mapped. Gravity reveals the presence of mass. Light does not always reveal where it is hiding. Some large-scale alignments in the sky seem unlikely by chance. Cosmology assumes that, on the largest scales, the universe should look statistically similar in every direction. That idea has passed many tests. Yet a few patterns have raised eyebrows. Certain features in the cosmic microwave background appear to show alignments across wide angles, and some analyses have found correlations that look stronger than a simple random universe would predict. These anomalies are debated because subtle systematics can create misleading patterns. Foreground contamination from our own galaxy can also imprint structure that looks cosmic. Even the act of analyzing many patterns can create false surprises, since some will look unusual by luck alone. Still, the discussion matters. If an alignment held up beyond all reasonable doubt, it could hint at new physics or unexpected cosmic history. At minimum, it forces careful thinking about data, assumptions, and statistics. Sometimes the universe challenges us, not with noise, but with hints that coherence might hide in places we expected randomness. The universe's largest structures challenge how quickly order can form. Galaxies gather into groups, groups gather into clusters, and clusters trace out superclusters and long filaments. When surveys map these structures across enormous volumes, they sometimes find features that feel surprisingly vast and coherent. The puzzle is not that structure exists. Gravity makes structure inevitable. The puzzle is how quickly matter can organize into very large patterns, given the age of the universe and the initial conditions we infer from the cosmic microwave background. Astronomers test this by comparing observations to simulations that start from early fluctuations and evolve forward under known physics. Usually the match is impressive, which is a triumph of cosmology. Yet the most extreme structures remain useful stress tests. They push us to check selection effects, measurement uncertainties, and the assumptions inside simulations. They also invite deeper questions about how we define a structure in a noisy cosmos. The biggest patterns in the universe are not just scenery. They are benchmarks for the story of growth itself. Cosmic strings are hypothetical cracks in spacetime that might still exist. If the early universe changed phase the way water freezes, it might have left behind thin defects, lines where the change did not match up perfectly. These would be cosmic strings, not made of atoms, but made of trapped energy in the fabric of space. A single one could be incredibly massive for its width, yet so narrow that it would slip through planets like a needle through fog. We would not see it glowing. We would notice it by what it does to light and matter. It could bend distant starlight into duplicated images, or it could send out brief bursts of gravitational waves when loops form and snap. Searchers have looked for these signatures in sky surveys and in gravitational wave data. No confirmed detection exists yet. Still, the idea remains compelling because it would be a surviving fossil of the universe's earliest moments. Primordial black holes could be dark matter, but constraints are tight. Most black holes form when stars die, but there is another possibility. In the first instance after the Big Bang, dense regions might have collapsed directly into black holes, long before any stars existed. These primordial black holes could range from tiny to enormous, depending on the physics of the early universe. If enough of them formed, they could account for some or even all of the unseen mass that shapes galaxies. The challenge is that they leave traces. A population of compact objects would bend background starlight in brief microlensing events, and it could disturb star clusters and galactic structure in ways we can test. Very small ones would also have evaporated by now if Hawking's idea is correct, which limits which masses remain plausible. As surveys improve, many mass ranges have been ruled out, yet a few windows remain interesting. It is a bold idea because it turns a mystery of matter into a relic of the universe's birth. Extra dimensions could hide, affecting gravity at tiny scales. We experience 3 dimensions of space, yet some theories suggest there could be more, curled up so tightly that they escape ordinary notice. If extra dimensions exist, they might change how gravity behaves at very short distances, perhaps making it stronger than we expect below a certain scale. That possibility has motivated careful tabletop experiments that measure tiny gravitational forces, searching for deviations from the usual inverse arc. Square rule. Particle accelerators also contribute by looking for signs of missing energy that could imply gravitons leaking into extra dimensions. So far, nothing definitive has appeared, and the constraints have become stringent. Still, the idea persists because it could help explain why gravity is so weak compared with other forces. It also offers new ways to connect the physics of particles to the geometry of space itself. Hidden dimensions would mean the universe is roomier than it feels, with structure folded into scales we have barely begun to probe. Quantum gravity remains unfinished, and black holes keep pushing us. Modern physics has 2 great frameworks. Quantum theory rules the small, and general relativity rules the large and massive. Each works beautifully in its own domain, yet they clash in extreme conditions where both should apply. Black holes are a prime example, because they combine immense gravity with regions that demand quantum rules. The problem is not a missing decimal point. It is that our current mathematics cannot fully describe what happens when space-time itself should have quantum behavior. Researchers explore several approaches, including string theory, loop quantum gravity, and ideas that treat space-time as emergent from deeper quantum K. Ingredients. Each approach captures some pieces, and each faces open challenges. Observations are starting to help. Through precise studies of black hole environments and gravitational waves that test relativity in strong fields. Still, the key tests may require new kinds of measurements or entirely new thinking. Quantum gravity is unfinished because nature is asking questions we have not yet learned how to answer. The multiverse is a serious idea, but hard to test. Some cosmological models suggest our universe may be one region within a larger reality, with other regions that have different initial conditions, even different physical constants. This can arise in certain versions of inflation, where expansion continues in some places while ending in others, creating many bubble-like domains. It can also arise in frameworks where the laws of physics allow many possible vacuum states. The appeal is that it might explain why our universe has properties that seem unusually suited for complex structure, because we would naturally find ourselves in a region where conditions allow observers. The problem is evidence. If other regions are beyond our cosmic horizon, direct observation may be impossible. Researchers therefore look for indirect tests, such as specific patterns that collisions between bubble universes might leave in the cosmic microwave background. Such signatures are difficult to distinguish from ordinary cosmic variation. The multiverse sits at a fascinating boundary where theoretical elegance meets the strict demands of testability. Vacuum energy predictions and observations disagree by an absurd amount. In quantum physics, empty space is not truly empty. Fields have a baseline energy, and naive calculations suggest that this vacuum energy should be enormous. In cosmology, however, the observed acceleration of the universe implies a much smaller energy density associated with space. The mismatch is not a small embarrassment. It is one of the largest known gaps between theory and measurement in all of physics. Something about our understanding is incomplete. Perhaps different contributions cancel almost perfectly, for a reason we do not yet grasp. Perhaps our method of calculation is not appropriate when gravity and quantum fields are treated together. Perhaps there is a symmetry or principle that forces the vacuum energy to be small. Many proposals exist, and none are universally accepted. What makes this mystery so striking is how personal it is to the cosmos. The large-scale fate of the universe seems to depend on an energy we struggle to define, in a space we once considered nothing at all. Some constants seem finely tuned for complexity, and nobody knows why. The universe runs on a set of numbers, like the strengths of forces and the masses of fundamental particles. If some of these values were different, the cosmos might still exist, yet it could look radically unlike our own. Stars might burn too quickly, or fail to ignite. Stable atoms might be rare. Chemistry might lose the variety needed for complex molecules. This observation is sometimes called fine-tuning, and it invites several interpretations. One view is that the constants must have these values due to a deeper, undiscovered theory. Another view is selection. If many universes exist with different constants, then observers naturally appear in the rare ones where complexity is possible. A third view is caution. Our knowledge of how changes propagate through physics may be incomplete, so the range of viable universes could be wider than we think. What remains is the feeling of standing before a control panel of reality, seeing dials set just so, and realizing we do not know who or what set them. Time's arrow emerges from entropy, yet the beginning is puzzling. In daily life, time has a direction. Eggs break, but do not unbreak. Smoke spreads, but does not gather itself. Physics explains this through entropy, the tendency for systems to move toward more probable, more disordered states. The surprise is that the fundamental laws do not strongly prefer a direction. Many equations work nearly the same forward or backward. That means the arrow of time must come from conditions, not from the basic rules. It points back to the early universe, which appears to have started in an unusually low entropy state. That is the real mystery. Why was the beginning so ordered, so special, so unlike a typical random configuration? Different ideas attempt to answer this, including cosmological models with bounces, or proposals where the early universe had a specific geometric style. Simplicity. None are settled. The arrow of time feels obvious, yet its deepest explanation may be written in the very first moments, in a boundary condition we still do not understand. The far future of the universe depends on dark energy's true nature. If dark energy is constant, expansion will continue to accelerate, and distant galaxies will slip beyond what we can ever observe. The cosmos would grow colder and darker over unimaginable spans of time, as stars fade and matter becomes more diffuse. If dark energy changes with time, the story could be different. Acceleration might weaken, or it might strengthen. In some scenarios, an increasing dark energy could eventually overpower all binding forces, separating galaxies, then star systems, and in the extreme, even tearing apart atoms. In other scenarios, dark energy might reverse sign or behave in ways that slow expansion, which could alter long-term structure and destiny. Right now, observations are consistent with a constant form, but uncertainty remains, and small differences matter enormously over cosmic time. This is why measuring dark energy is not just bookkeeping. It is a way of asking what kind of ending the universe is headed toward, and whether the ending is quiet, dramatic, or something we have not imagined. The biggest mystery may be why the universe is comprehensible at all. The cosmos is vast, indifferent, and often violent, yet it is also describable. Simple equations can predict eclipses, explain spectra, and reveal invisible mass through gravity. Patterns repeat, laws hold, and mathematics maps onto reality with uncanny effectiveness. That success is so familiar that it can feel normal, but it is not logically guaranteed. The universe could have been chaotic in a way that resisted compression into rules we can discover. Instead, it offers regularities that minds like ours can grasp, test, and refine. Some philosophers argue that comprehensibility is partly selection, because beings capable of asking questions must evolve in a world with stable patterns. Scientists often answer more pragmatically. We learn because the universe has structure, and our brains are pattern-seeking tools shaped by survival. Still, the feeling remains. We are made of star-forged atoms, living on a small world, and somehow we can understand galaxies, particles, and space-time. That bridge between mind and cosmos may be the most astonishing link of all. As we come to the end of our journey through cosmic mysteries, you can let the ideas settle like stardust. We wandered through a universe where most of what matters cannot be seen. We traced the strange influence of dark matter as it shapes galaxies, and the even stranger push of dark energy as it stretches space itself. We listened for ripples in space-time from colliding black holes, and we imagined neutron stars with interiors that challenge every rule we know. We visited worlds beyond our sun, some losing their skies, some locked between endless day and endless night, and some drifting alone through interstellar dark. We skimmed the ancient afterglow of the early universe, and we followed questions that still have no final answers, from missing antimatter to the possibility of life elsewhere. If you enjoyed this drift through the cosmos, you might like to tap like, subscribe, or leave a small comment. It helps this channel find others who need a calm place to land. And if you happen to still be awake, there will be another video waiting on your screen. You can let it carry you onward, one more slow step into wonder. But for now, you do not need to solve anything. Let your breathing ease. Let your jaw unclench. Let your shoulders sink down into the support beneath you. Picture the sky above a quiet world, wide and patient, while the universe continues its long unfolding without asking you to keep up. You have done enough for today. Sleep well and good night.